Hello students, welcome back. We completed section 1. Now let's go to section 2. Finitely generated abelian groups. Before that, however, we need some preparation. And the preparation begins with the intersections. This is what we want to establish. An intersection of a bunch of groups is again a group. I should have said subgroup because we want to consider the same algebraic operation. So let's begin with a B group G with a group structure, of course, and then let's consider a collection of subgroups, H1, H2, H3, and so on, and that may not be finite. You see, this index at capital I can be arbitrary. In any case, the intersection is again a group. That's what we want to prove. Now, how do you do that? Well, remember three things: closed under the group operation, identity, and inverse. And then another key technique here is, what do you mean by something is a member of the intersection? That means it's a member of all HIs. With those, you can prove this easily. Try it. Stop the playback and try it on your own. Any success? Well, let's see. The first step, close under the group operation. This is what we want to establish. Choose a pair of elements from the intersection, and the product also belong there. What do you mean by a member of the intersection? That means these are the members of all HIs, and each HI is a subgroup, so the product belongs to each HI, every HI. Therefore, the product belongs to the intersection. So, intersection gives us all, and then for all, we can use all these group property, and then eventually we are coming back to the intersection. So all versus intersection, that's a key technique. How about the identity? Well, that's really trivial. Identity exists for all subgroups, so clearly. Still, intersection versus all. How about the inverse? Again, the same deal. Select any element, and we want to find the inverse from there, and the idea is the same. Member of the intersection, that means it's a member of all HI, no exception, and then each HI is a subgroup, so we have inverse there, and then that applies for all HIs, so we have the intersection again. Same idea, all versus intersection. So that completes the proof. The intersection is again a subgroup. Not only that, it is the largest subgroup contained in all HIs. In terms of the set inclusion, of course. Interesting. Intersections make things smaller, but what do you mean by the largest? Comparatively speaking, if there is another subgroup contained in all HIs, then that subgroup is contained in the intersection as well, making the intersection the largest possible. The proof? Well, proof is really trivial because the set inclusion part is basically really trivial, you see. Any element of K belongs to all HI, but then that element belongs to all HIs, so it belongs to the intersection. So all elements of K belong to that intersection. Yeah, the set inclusion is trivial. The question is whether this is a subgroup as well, but then again, we did it as well, so there you go. I wouldn't even call it a proof, just a trivial observation. Still, make this observation. not only this is a subgroup, it's the largest subgroup contained in all HIs. But then again, here's another aspect. If the collection is this collection of all subgroups containing a certain set S, and that doesn't have to be a subgroup or anything like that, just a set, which we are going to call a generating set in 2.2, then the intersection is the smallest subgroup that contains the set S. Previously, the largest, now the smallest. What's going on here? A change of viewpoint. Previously, we were looking at HIs, looking on HIs. So from HIs and no other restriction, the intersection is the largest subgroup contained in all HIs. But this time, we're looking at it from S. And then another special condition, the collection is the set of all subgroups containing a certain set S, which we are going to call a generating set. Then under that special circumstance, the intersection is the smallest subgroup that contains a set S. How do you prove that? A little bit trickier. This one was just trivial observation, but this is going to be a little bit trickier. Let's rewrite it in symbolic fashion like this. If there is any other subgroup of G that contains S, then that must be larger, making the intersection the smallest. By the way, previously I used index expression, i's rank 1, 2, 3, 4, and so on, possibly toward infinity or more. But this time I didn't use those ordered expression. This is a collection of all subgroups containing S, so I just put that condition here. These H's are subgroups of G that include S. Can you read that? So that's the condition. And look at this condition versus this one here. They are the same. Do you see that? Just the character is different, H versus K. In other words, K is actually a member of that collection. You see, K is a subgroup of G that contains S. Then it's a member of all subgroups of G that contains S. And the intersection is the intersection of all the subgroups in this collection, and K is one of them, so the intersection must be smaller, you see. A little bit trickier, yes, and then went a little bit more about the set theory, and we are doing possibly infinite intersections, so it can get a little bit trickier, but I hope you understood all those. In any case, remember this. If you look at this intersection from HIs and no other restriction, then the intersection is the largest subgroup contained in all HIs. If you look at it from a certain set, and the collection is not just some subgroups, but the collection of all subgroups containing that starting set S, which we call the generating set, by the way, in 2.2. In that case, the intersection is the smallest subgroup. So the intersection has two aspects. It's the largest and the smallest at the same time, but that's because of the change of viewpoint. Okay, so much for 2.1, and we're going to discuss 2.2 in a separate video. See you soon.